Hey guys, this is Christopher Manning, and I'm interested in the Plutus core system and how the smart contracts are run through Cardano using the UTXO extended model, and it seems to be just as good, if not better, than Bitcoin. So here's an example of something inside of Plutus core and the smart contract system. It's one of the examples inside of the Plutus Playground that specifically is the game that runs two words and compares the two to see if the words match. The blocked word being the data script and the guessed word being the redeemer script. So let's get started by explaining on how this runs. We'll start with the top section here, which involves the one of the let's say pieces of the guessing game, which is the hashed string, which will be the string you set inside of the locked function down here, where it says make data script. So that being said, when you're making the data script, for the data script, it'll take a string and return a data script. And so for the string, we'll call it word. And as for the word, actually, before we start with that, let's go with this first. Let's say we'll start with the data type hash string, and hash string is a byte string. So define data type for hash string being a hashed byte string. So that's what this is. It's like setting up a data type for the to lift inside of the Plutus compiler for compile time when we go to use the logic later on right here. So, um, so now that the data type of the byte string that's a hash string is lifted inside of the Plutus compiler for the compile time, we can manipulate the hashed. We can stick a hashed word inside of this lifted data type of Plutus, which will be eventually inside of the blockchain. And for the data script, the string once again returns a data script. So as for the string, we'll call it word, and we'll let hash word, which is a new variable that we're creating inside of this function, equal the SHA-2 256 of the byte string, which is what this does. It creates a byte string of a word where you can find the definition inside of here. That's what is inside of this library. It packs the word into a byte string, so it changes all of the characters in the word into 8 bits. So that's like for each string character, and then and that word being the word that you stuck inside of the string when the function was called. So now you have a hashed byte string word, and it's stuck in hashed word. So now we can continue, and in data script, which is a new function that we just call out of nowhere, ledger.lifted, and then hash string hash word. So this assigns the hash word with the hash string make lift type defined earlier. So once again, we created a lifted type here that's inside of our blockchain compiler time, and this is a new variable using that data type that has also been lifted inside of the data script, which is what we're going to use in our compiler or redeemers, or rather a validator script. This is where all of the compiling happens, and the Plutus core comes into play. So now we can continue, I guess. So let's say, so now we have a data script, which would be just a word that's hashed and stuck inside of the data type that has already been lifted, and we lift that as well. So like that's a whole new um, data type basically, or part of like a, I don't know what the word is, man. Like just a new part, man. Like it's just some new thing that has the type of data string and the name hashed word, and it's lifted with all the rest of it in data script, which is kind of something that I don't really get. You know, it's Haskell, so it's new to me. You know. So next, we can continue down here, which data clear string equals clear string byte string. So now we got a clear string, which basically is a type that we're going to lift, and all it is a byte string. So, and that's nothing special. Like it's not a hash string. I mean, it's the same thing as before. It's just a byte string, but we're not going to manipulate it with the SHA-256. As you can see here, we're just going to leave it with a byte word, basically like a byte string word, and then we'll lift that byte string word inside of the compiler as the redeemer script. So so now that we have now we have the data script and the redeemer script, and that can be explained in other videos, but it's pretty much self-explanatory right here. It's this is the client, where the client, or actually this is the server, where the server is giving the hashed word. You have to, and then this is the client, where you the user have to guess the word. And then here is the blockchain, where it's the middleman, basically, like what we're trying to replace big companies with. Is basically like this is what is doing the computation that is basically changing the outputs of your, not changing any output, it's just taking in input and then giving you like an if-else statement in this case, where you can compare the two strings using one of Plutus's functions here, p dot equals byte string. So this function obviously just takes a string and compares it with another string. So as for this first string, well, let's begin with the beginning here. So the game validator is a validator script, and game validator equals validator script. So that's how you begin all of your compiling of Plutus core. Is validator script, and then you got parentheses ledger dot from compiled code, and then these dollar signs, which is Plutus functionality, and so that basically begins the first line of Plutus, which involves the compiler. So this is where the Plutus compiling comes in after this little special set of characters here. And then we can begin with the lambda function, which takes two lifted data types that we have created earlier, and as you can see, it's a clear string and hash string, and that's exactly what we wanted. We can create as many of these data types as we need, as explained in vesting example right here. Let's see, vesting, or actually let's try crowdfunding. Let's try that one. Yes, as you can see, there's more than or there's more than two in this case. So like obviously, like I'm pretty sure you can have as many as you want, like, and separate them in different smart contracts and enjoy your little like network of information somehow. Anyway, so that's really cool. You can create as many data types as you need within a lambda function that is basically like the header of your file, or the header of your little code, little snippet here, which is like nice and structured and not ugly looking, you know, like C++ or anything like that. And then so now we can go and continue. Let's see. All right. so after when this function is called, this is always required in the each smart contract, as you can see. It takes one right here, takes one right here. So in every example, you'll find that this exists. So this is basically a required function, which is just like whatever. Like I guess I don't know what it is. Like it's the beginning of the Plutus. Um, again, like after once again. Okay, this is the beginning of the compile time. This is the beginning of the like body of the Plutus. So like there you go. And so within the body of the Plutus, if the equal byte string is actual with the SHA-256 version of guess, so what's happening here is it's creating a SHA-256 version of the guess to compare with the actual hashed string. So if these two strings, which are now like a hashed string, which is like a long string of characters that don't make any sense to the naked eye, if they compare correctly, as in like all of the characters within it, including numbers and dots, whatever it could be, match exactly to how the other string matches, like the actual or the guess, then what we want to do is continue running this function or whatever, like just basically like continue operation, like do whatever you requested, and else error wrong, like so else give us an error, remind us that what happened, and so that's like an error check basically. And so that being said, so now that we have the three functionalities involved here, you can or the three bare bones of any smart contracts, basically, like the data script, the redeemer script, and the game validator. Next is you got the actual functions that are played inside of the Plutus playground specifically for now, and also later on if these functionalities are going to stay the same when the full implementation is handed out to everybody, or whatever the word is. You know what I'm saying? All right, so game address. We obviously want the address so that we can start watching the game when we're ready to watch the game. So like every smart contract in the Plutus Playground requires you to watch the contract. So basically each wallet has to begin by watching the game address, or else the output won't be displayed, and it's kind of like a mind-boggling experience if you don't know what's going on. So anyway, let's see. So now we got game address, and it's just the takes the type address, which I don't know, like I guess this apostrophe means that you've defined a new type of address somewhere in one of these libraries, I guess, and I don't know, maybe it's in, I don't know, I gotta learn about that. Find it somehow, like it's gonna be a pain, but not too much though. All right, and then so for the game address, you want to get for what it returns as game address, you want to give it the game validator, the address to the game validator. So like you might wonder, why isn't it taking an address to the data script or the redeemer script? Well, that's because the data script and the redeemer script are the client and the user, or I mean rather the host and the client, and so we don't want the address to the host or client because that's like biased, obviously. Like we don't really care like where they're located. So what we want is the address of the actual blockchain, like compiling whatever, like Plutus. We want the third party address. We want the game. We don't want the fucking people. That's like the whole idea. So we get the address of the game, and we stick it inside of a little special function called game address. And now we can use that later, so that anytime we call game address, it'll have all this, it'll have the address basically of the game value. And so now let's just we'll do this one real quick so we can get it out of the way. So like I said before, we have to watch it the game with with each wallet. So you just click watch game or start game right here, and on wallet 1 and on wallet 2 on the Plutus playground, which is right here. And so like I said, just once again, you just let me start from the beginning. So you go start game with wallet 1, start game with wallet 2, and then so now you have that set up. That's all you needed to do. And what that does is it basically runs this function, which is a Plutus playground function that is simulating watching the blockchain as it's taking place. So I don't know if it'll be the same when it actually comes out, but whatever. It's as easy as that right now. So now we're watching so now we have to give it a parameter to watch. So the parameter being the game address, and so you have to learn about this function in the API somewhere in order to understand why it takes this. But it's easy to just look at it and say, oh yeah, start watching the damn game address. Like okay, it makes sense. And the game address is a validator, which is a third-party system that you can trust, and you don't have to trust any of these guys because they're gonna make some shit up at one point. But this guy can't really make shit up because he's gonna hash his word, and if you hash your word, you can't really change your hashed word, and that's the whole point of like blockchain right there. So and now we move on. Okay, so this function here is a string, or what it does is it locks your funds. So it's basically the beginning of the game. Like you're gonna lock the word. You're gonna put some money in, and you're gonna have it with the data script, and the data script is gonna be the word. And once again, like the UTXO extended model, which every transaction in Cardano involves a value and a data script. So that's what makes it really cool compared to Ethereum, which is an account-based model system and runs in a different way. And I don't really care for it because it's fucked up, and it fucked them. They suck. So fucking like UTXO extended model said it's in data script, and in each transaction you take, it'll be given some sort of information. And it could be like no information, like you could just pay into something like, no information involved. I don't know if they're going to have something for that where you can just like say no thanks, we don't accept money for no data script or not. You know what I'm saying? But right now it's like you have to have a data script and you have to have a value. And it could be 0, 0, 0, 0, everything, but like that's what it is. So within the data script, it's the word basically. So the word is your word that you stuck in through your locked function. So a word that is also run through the data script function here, which basically does the whole hashing of the word here and sticks it inside of data script. So that's really cool because so now you can go pay to script, which is a function that is required from or not required. It's just a function that, like I said, like you're going to send a value and a data script, no matter what the transaction is. So now that the transaction is taking place, you require the address, right? And then you also require a value, which the value is obviously, in this case, is going to be what you're locking into the smart contract. So that's interesting that, like it matches exactly what I said, that it requires value. And then also it requires a data script. So your data script being, it could just say data script and then, like nothing or whatever, like how this is explained right here. See, in data script, it could be like a blank data script and with nothing in it. So, but now in this case, it's a smart contract. So it has the word that it's going to use. It's going to hash this word, and it's going to lock it inside of the smart contract, basically by just by the turn of events. Like it's basically like, so when you like lock wallet 1, it's just step number 3. You know, like I don't know how it's gonna be on the blockchain, like time wise, or how they're gonna separate locking, you know, inside of a smart contract from the guessing part of the, you know, like, I don't know how it's gonna be, but for now this is like what it looks like. It's just, you're locking it in, and it's one step inside of the process, and the next step is guessing, and obviously you're guessing the right word, right? Like so that what you're doing is collecting from script, and that script you're collecting from is obviously the address of the game validator. So you need an address. That's the function collect from script, and it also needs a redeemer script, because in order to collect from script, it requires a redeemer script, which is very useful in the sense, because maybe like you don't need a redeemer script, or like you can just write in your game validator, if redeemer script is empty, then execute, else error, you know, so it'll work anyway, and you don't have to worry about any sort of logic. But obviously we care for some logic because we're guessing for the word. So the word inside of the redeemer script is being changed into a hashed word. Yeah, so yeah, it's right here. So it's being changed into the hashed word here, as it's been given a clear string data type, which the word in make redeemer script goes all the way up here to word in redeemer script, and it gets stuck inside of the redeemer script as a clear string. So so then it has to be, and then once it's been stuck in the redeemer, or once it's been lifted in the in the redeemer script as a clear string, we can manipulate it with the guess variable here, and change the guess variable into that hash, and then that hash is going to compare with the actual hash of the beginning. So this is kind of cool, because like with a dice contract, and you know, any gambling contract, this is where that comparison comes into play, and why it runs so smoothly, and just looks really nice. I don't know. I think this is what makes the dice game like what it is, you know. So like, and obviously because it's like a blockchain, you know, like, and that's money, man. That's where it's at. So freaking, it's comparing the two hashes together, and that's about it. That's like, so when the redeemer script has completed through the blockchain validator, the game validator, what will happen is you'll receive the funds. It'll basically run the whatever, it'll collect the script, basically, like whatever you're asking of the blockchain, basically. Like, so you can ask any function, like you can say lock word, you know, require, and then like you can just pay to the script and give it a word, and that'll be considered locking. And then when you guess, you can just collect from script and guess the word, and then that'll be considered collecting. So it's like, that's it, you know what I mean? And then so you got these functions here, which basically give you the buttons that allow you to click for the functions on Plutus Playground. So it's required, just a thing. Looks cool. It doesn't matter. I know it's weird looking, but whatever. All right, let me show you what it can do now. So with the same code, as you can see, like nothing changed. Just a bunch of comments. We can click compile compile again, and then we'll do all this again. Okay, so we can go start game. This will, and that will start watching the address for both wallets. So both wallets now can visualize what's going on in the blockchain with the code and the logic. So now we can begin the logic, which will be the lock and guess. And as you can see, compared to our functionality here, which is cool, our lock takes two values, a string and a value, which your string being the word, your value being how much you're paying into the contract. And as you can see, it displays two boxes for us to type things in, a string and a int, which will be our value. And that's really cool because, I mean, like, come on, like, it's just extra boxes to do things. And I mean, we can just do some crazy shit, you know? You can have plenty of anything you want, you know? It's just amazing. Learn Haskell and you can, it's similar to C, like, you just have to, like, fix your knowledge into a functional language and take that same, like, programming, like, inspiration and stick it inside of Haskell, and it's easy. So easy, man. But I'm still learning, so I can't say that. All right. So now we go. For the string, we say hey, and then the value we can put like 3. And then for the guess, we'll give it the incorrect word, just so we can see what it looks like. So as for the incorrect word, we obviously get wrong because we set it up in our compiler here to display the a trace error, which so the error requires a function, which within the function we can give it another function that displays the wrong in quotes, and then end it with a function, or end it with like a little like function call that's empty, that from calling ptrace, I guess. I don't know if this is like an extra function call or not, like this one is, where it cuts out, you know, or if it's part of the, actually it could be part of the error thing. I don't know. I just gotta learn about it. Some interesting questions. But okay, so now you can see why it turned wrong, is that the logic obviously was incorrect, because our equals byte string actual did not equal our guess, which has been turned into a SHA-256 so that it can compare. All right, now we'll give it the correct answer, which will be y, and then we'll just change the value. Now we'll leave it. Evaluate. So now you can see there's no error in our transactions, and we get all these cool little squigglies, you know. I mean, look at that. I mean, that's some art right there, man. Holy shit. But anyway, so now you can see that the transfer has happened correctly, in the sense that the wallet 1 has locked or had paid to script 3 Cardano, and then wallet 2 had redeemed the script by collecting from script using the redeemer script, and it had matched with the logic, and the function had completed the compile time right here. But you know, like once again, I gotta find out like if this is any sort of similarity to this, or if it's just part of, if this right here is just part of one of these functions here, because that could be the case. And you know, in that case, it'd make it a lot easier to understand, but it would kind of make it difficult to understand. I don't know. Fuck it. If anybody's got an answer for me, let me know. So thank you. Let's see. I'll leave it right there. Okay. Thank you so much, guys. Let me end the video. Have a great day.